Question 1. What is the most likely root cause when a heat pump system in cooling mode shows normal head pressure but extremely low suction pressure while airflow across the evaporator coil remains unchanged? A malfunctioning indoor blower motor causing low airflow. B. A defective reversing valve leaking internally. C. A restricted metering device or plugged TSSB. D. An overcharged refrigerant system. Answer. Correct answer, C. A restricted metering device or plugged TSSB. Explanation. Low suction pressure combined with normal head pressure and steady airflow across the coil strongly suggests that refrigerant flow to the evaporator is restricted. This is commonly caused by a plugged thermal expansion valve TXB or debris blocking the orifice in a fixed metering device. The metering device regulates refrigerant flow. If restricted, it starts evaporator, reducing vaporization and causing suction pressure to drop. Overcharging would increase both pressures. Internal valve leakage affects both pressures unpredictably. Refer to ASHRAE fundamentals and a CAM manual D for pressure diagnostics. Question 2. Given the circumstances, ISIS Green's heat pump runs the auxiliary heat strips frequently, even in mild weather. A technician verifies the refrigerant charge is correct, airflows within specs, and sensors are calibrated. What should the technician check next? A. Dirty outdoor coil preventing heat rejection. B. Time temperature defrost control malfunction. C. Thermostat configured incorrectly for heat pump use. D. Low voltage transformer undersized. Answer. Correct answer, C. Thermostat configured incorrectly for heat pump use. Explanation. If a thermostat is incorrectly set up, for instance, set to electric heat instead of heat pump, auxiliary heat will energize unnecessary. This is a common mistake during installation or replacement. Time temperature controls or coil cleanliness would impact defrost or efficiency, not trigger unnecessary strip heat alone. See neck thermostat wiring guidelines, thermostat programming manuals, and a CAM manual S for proper configuration. Question 3. In light of recent developments, a technician suspects a heat pump is undercharged and measure a subcooling of 1 IC and superheat of 29 IC during cooling operation. What conclusion can be drawn based on these readings? A. System is likely overcharged. B. Metering device is stuck closed. C. System is critically undercharged. D. Compressor is short cycling. Answer. Correct answer, C. System is critically undercharged. Explanation. High superheat 29 EGF with very low subcooling 1 EGF strongly indicates insufficient refrigerant. The evaporator coil isn't getting enough liquid, leading to overheating of refrigerant gas, while the condenser can't maintain proper liquid seal. Superheat 20 EGF is abnormal. These symptoms align with EPA 608 leak indicators and ASHRAE 34 standards. Refrigerant diagnostics. Question 4. When analyzing a heat pump system, the reversing valve fails to switch from heating to cooling. Voltage is present at the solenoid coil. What is the most appropriate next diagnostic step? A. Replace the solenoid coil immediately. B. Check the pressure differential across the valve. C. Cycle the thermostat multiple times. D. Remove and clean the valve body. Answer. Correct answer. B. Check the pressure differential across the valve. Explanation. Even if voltage is applied, the reversing valve needs a minimum pressure differential, 60 psi, to shift positions. A low charge condition or faulty compressor could prevent this. Replacing coils without verifying pressure is premature. Per SAES guidelines and OEA reversing valve schematics, proper operation depends on mechanical pressure differential, not just some actuation. Question 5. As illustrated by the case of Istaleri, who recently noticed that his heat pump makes a loud hissing noise followed by a drop in indoor temperature during heating mode, which then recovers after a few minutes. This cycle repeats every 45 minutes. What is the most likely cause? A. Low refrigerant charge. B. Compressor bearing failure. C. Normal defrost cycle operation. D. Sticking contactor relay. Answer. Correct answer, C. Normal defrost cycle operation. Explanation. Heat pumps enter defrost periodically to remove frost from the outdoor coil, temporarily switching to cooling mode. Hissing from the reversing valve and drop in indoor heat are typical if it happens at regular intervals. 3090 minutes is likely time temperature defrost system working as intended. See a CAM manual H&OEM defrost control board document for expected cycle characteristics. Question 6. From a practical standpoint, which of the following best explains why an oversized heat pump system may lead to poor humidity control in cooling mode? A. Compressor operates at higher pressure. B. Evaporator coil becomes too cold, increasing latent capacity. C. Short cycling prevents adequate dehumidification. D. Indoor fan motor is oversized, causing airflow imbalance. Answer. Correct answer. C. Short cycling prevents adequate dehumidification. Explanation. Oversize systems reach set temperature quickly but don't run long enough to adequately remove moisture from the air. This results in clammy comfort complaints. Latent cooling requires longer runtimes. Refer to Manual J, load calculations, and Manual S, equipment selection, which emphasize matching equipment capacity to building loads to ensure humidity and comfort. Question 7. In the context of defrost control diagnostics, a technician notices that the outdoor coil is covered with ice and the unit hasn't entered defrost. The time temperature defrost board shows that time conditions are met. What is the next logical step? A. Replace the defrost control board. B. Inspect the defrost sensor or thermistor. C. Adjust the refrigerant charge. D. Increase fan speed to melt the ice. Answer. Correct answer. B. Inspect the defrost sensor or thermistor. Explanation. If time conditions are satisfied but the board doesn't initiate defrost, the temperature sensor thermistor is likely not detecting the necessary coil temperature. These sensors typically require the coil to be below threshold e.g. 30 to allow defrost. Faulty or open sensors will prevent defrost initiation. Refer to OEM control board specs and RCESA troubleshoots. Question 8. Considering the evidence, is Ortiz observes a dual-fuel heat pump system switches to fossil fuel even when outdoor temperatures are moderate. What is the most likely configuration error? A. Outdoor coil temperature sensor is miswired. B. Fossil fuel lockout is set too high. C. Crankcase heater stuck in RON mode. D. Indoor fan relay is defective. Answer. Correct answer. B. Fossil fuel lockout is set too high. Explanation. Dual fuel systems switch from heat pump to fossil fuel when outdoor temps drop below a set lockout point. If this point is incorrectly set e.g. 55 deg instead of 35 deg, the system uses fossil fuel unnecessarily. This reduces efficiency and increases costs. Refer to RE dual fuel integration practices and thermostat programming guides for lockout temperature settings. Question 9. Across different scenarios, technicians must evacuate systems properly before charging. What is the minimum vacuum level and holding time required for proper evacuation of a heat pump using POIL and HFC refrigerant? A. 500 microns, hold for 10 minutes. B. 1000 microns, hold for 5 minutes. C. 250 microns, hold for 2 minutes. D. 200 microns, hold for 1 hour. Answer. Correct answer. A. 500 microns, hold for 10 minutes. Explanation. Best practice per EPA 608 and ASHRAE 147 mandates pulling a vacuum to at least 500 microns with no rise above 500 microns for 10 minutes, indicating absence of moisture and leaks. POIL is hygroscopic, so thorough evacuation is critical. Holding at 1000 microns or for short duration inadequate and can lead to system contamination. Question 10. The correlation between suction line icing and superheat readings in a heat pump system helps diagnose metering device issues. If suction line is iced and superheat is measured at 5 deg, what does this imply? A. The system is overcharged. B. There's faulty blower motor. C. The TSV is stuck wide open. D. The evaporator coil is dirty. Answer. Correct answer. C. The TSV is stuck wide open. Explanation. A superheat of 5 deg indicates nearly saturated vapor exiting the coil. Too little heat added, combined with suction line icing, this shows excess refrigerant is flooding the evaporator, likely due to TSV stuck open. Dirty coils and airflow problems raise superheat, not lower it. Refer to CAM Manual RS and Refrigeration Service Engineers Society standards for TSV diagnostics. Question 11. Through careful analysis of a heat pump system that is short-cycling, technician Mr. Nolan finds that the low-voltage transformer is warm to the touch and the contactor is chattering. The system occasionally restarts but then shuts down again quickly. What should Mr. Nolan inspect first? A. Contactor coil resistance. B. Heat anticipator setting on the thermostat. C. High voltage breaker size. D. Low voltage short or overload condition. Answer. Correct answer, D. Low voltage short or overload condition. Explanation. A warm transformer and chattering contactor typically indicate that the transformer is being overloaded, likely due to a short circuit or excessive load on the 24th control circuit. This may be caused by a shorted wire, stuck relay, or component drawing too much current. NEC Article 725 and NATE diagnostic protocols recommend low voltage circuits for integrity before replacing parts like contactors or thermostats. Question 12. Examining the consequences of refrigerant overcharging, what is the most immediate operational effect observed in a heat pump during cooling mode? A. Increased superheat and low suction pressure. B. Decreased subcooling and higher evaporator temperatures. C. High head pressure and reduced system efficiency. D. Lower discharge temperatures and improved efficiency. Answer. Correct answer. C. High head pressure and reduced system efficiency. Explanation. Overcharging increases the amount of liquid refrigerant in the system, raising condenser pressure, head pressure, and potentially leading to compressor overheating. It also reduces efficiency as the system struggles to reject heat. This contradicts EPA 608 best charging practices, which emphasize using superheated cooling methods to ensure accurate charge, especially fixed orifice systems. Question 13. When presented with a system exhibiting low airflow and high superheating cooling mode, technician is a TAN suspects. A ductwork issue. She confirms static pressure is above recommended levels. What is the most likely cause of this condition? A. Undersized indoor coil. B. Return duct restriction or blockage. C. Failed TSV sensing bulb. D. Outdoor fan motor failure. Answer. Correct answer. B. Return duct restriction or blockage. Explanation. High external static pressure suggests duct restrictions, most commonly on the return side. Restricted return airflow results in reduced coil heat exchange, leading to high superheat as the refrigerant under evaporates. This aligns with Manual D standards for duct design and airflow diagnostics, which emphasize the importance of correct duct sizing and layout for maintained airflow and system performance. Question 14. Taking into account the operation of an accumulator in a heat pump system, which of the following best describes its function? A. Ensures oil is returned to the compressor via suction line. B. Separates refrigerant oil from high-pressure liquid refrigerant. C. Prevents liquid refrigerant from entering the compressor. D. Stores excess refrigerant during the heating cycle. Answer. Correct answer. C. Prevents liquid refrigerant from entering the compressor. Explanation. The accumulator is placed in the suction line and is critical in preventing liquid slugging during the heating cycle, especially after defrost. It allows only refrigerant vapor to enter the compressor, protecting it from damage. Per ASHRAE HVAC Applications Handbook and OES specifications, accumulators are essential for system longevity and are commonly used in systems with variable refrigerant mass flow. Question 15. Under the assumption that a technician is conducting a vacuum on a heat pump system but notices the micron gauge fluctuating between 500 to 800 microns after isolating the pump, what does this indicate? A. The vacuum pump is contaminated with oil. B. The system contains excessive oil. C. There is likely leak or moisture in the system. D. The gauge is improperly calibrated. Answer. Correct answer. C. There is likely a leak or moisture in the system. Explanation. If the system cannot hold below 500 microns after isolation, it suggests either a leak or that moisture is boiling off, indicating insufficient evacuation. Per EPA 608 and ASHRAE guidelines, a system should hold vacuum under 500 microns for 10 minutes. Fluctuation above this threshold signals possible leakage or vapor contaminants like water inside the system. Question 16. Demonstrated by Garza's work on multi-stage heat pump, the second stage fails to energize even though indoor temperature continues to rise above the set point. The thermostat is programmed for multi-stage control. What should Garza test next? A. High-pressure switch continuity. B. Output signal from the thermostat. C. Compressor insulation resistance. D. Outdoor ambient sensor calibration. Answer. Correct answer. B. Output signal from the thermostat. Explanation. Multi-stage systems use for first stage cooling heating and for the second stage. If the second stage fails, verifying that the thermostat sends a 24 signal on is critical. If I is not energized, the second stage cannot engage. This test is essential before suspecting mechanical faults. Refer to OEM wiring diagrams and NEC 2017 low-volt signaling standards. Question 17. While examining a variable speed heat pump, the technician notices frequent system lockouts during low ambient heating. Data logging reveals that suction pressure drops too low during these events. Which component is most likely to require adjustment or replacement? A. Indoor blower motor. B. High pressure switch. C. Low pressure switch. D. Compressor contactor. Answer. Correct answer. C. Low pressure switch. Explanation. In low ambient conditions, suction pressure may naturally drop. If the low pressure switch is not calibrated for cold weather operation or has drifted, it may trip prematurely and lock out the system. Variable speed systems require pressure switches that accommodate a wider range of conditions. Refer to RE performance standards and OEM low ambient control guidelines for proper selection. Question 18. The evolution of heat pump defrost controls has led to more energy-efficient systems. Which of the following is a key advantage of demand defrost over time temperature defrost? A. It initiates defrost more frequently to protect the coil. B. It reduces reliance on outdoor thermostats. C. It eliminates the need for a defrost relay. D. It minimizes unnecessary defrost cycles. Answer. Correct answer. D. It minimizes unnecessary defrost cycles. Explanation. Demand defrost systems monitor coil temperature and/or pressure differential to determine the actual need for defrosting, initiating it only when necessary. This saves energy and wear on the system compared to time-based methods, which may initiate defrost even when not needed. Can manual H and DOE efficiency guidelines support using demand defrost for better performance? Question 19. Answer. Correct answer. C. When latent load is dominant. Explanation. In humid climates or spaces with high moisture loads, a slower airflow allows more time for the coil to condense moisture from the air, improving dehumidification. Higher airflow reduces contact time, which can leave air clammy. ASHRAE 62.1 Manual J and latent versus sensible load analysis emphasize balancing airflow for both temperature and humidity control. Question 20. To illustrate this point, a technician is asked to verify proper refrigerant charge using the subcooling method. The system uses her EE mean temperature is 9 degrees and manufacturer's target subcooling is 12 degrees. Actual subcooling is measured at 4 degrees. What conclusion should the technician draw? A. System has excessive charge. B. TSV is stuck closed. C. Condenser coil is dirty. D. System is undercharged. Answer. Correct answer. D. System is undercharged. Explanation. In TSV systems, superheat is controlled while subcooling is used to verify proper charge. A measured subcooling significantly below target 4 degrees versus 12 degrees indicates insufficient liquid refrigerant, meaning the system is undercharged. Dirty coils affect head pressure but not subcooling as directly. Refer to NAE exam charging procedures, OEM data plates and EP 108 guidelines for best practices in verifying charge. Question 21. From a historical standpoint, Dillard notices the auxiliary heat in. A heat pump system activates frequently even when outdoor temperatures are above 5 degrees. After verifying refrigerant charge and airflow, the technician observes that defrost cycles are occurring every 30 minutes, regardless of frost presence. What is the most likely cause? A. Sticking contactor energizing heat strips prematurely. B. Defrost control board operating in time temperature mode. C. Defrost sense shorted, forcing defrost too often. D. Thermostat anticipator set too high. Answer. Correct answer. C. Defrost sensor shorted, forcing defrost too often. Explanation. If the defrost sensor thermistor is shorted or falsely reading low temperatures, the control board may interpret that frost is present and initiate frequent defrost cycles. This can unnecessarily engage auxiliary heat during recovery. This aligns with OEM defrost algorithms and ACAM Manual H recommendations for verifying sensor function during root diagnostics. Question 22. To determine whether a system is overcharged, the technician observes a subcooling of 20 target 10 and superheat of 5 What conclusion should be made? A. The TSV is restricted. B. The system is critically undercharged. C. The system is significantly overcharged. D. The indoor airflow is too low. Answer. Correct answer. C. The system is significantly overcharged. Explanation. Excessive subcooling and low superheat indicate that too much refrigerant is present in the condenser, leaving little room for vaporization at the evaporator outlet. The TSV may still maintain low superheat, but overall efficiency and compressor safety are compromised. ASHRAE Refrigeration Handbook and EPA 608 outline charge verification best practices using superheated cooling. Question 23. The predominant theory suggests that refrigerant migration during the off cycle can lead to compressor damage. What component is designed specifically to prevent this conditioning? A heat pump system, A. Reversing valve, B. Accumulator, C. Crankcase heater, D. Pressure switch. Answer. Correct answer. C. Crankcase heater. Explanation. Crankcase heaters keep the compressor oil warm during the off cycle, preventing refrigerant from condensing and mixing with oil in the crankcase. Without it, liquid refrigerant may flash during startup, causing oil foaming and bearing wear. This is referenced in OEM installation manuals, NEC 430, and compressor design guidelines. Question 24. During the process of commissioning a new heat pump system, technician is Brooks pulls a deep vacuum. After reaching 300 microns, she isolates the pump and sees the pressure rise to 1200 microns in 5 minutes. What is the most appropriate action? A. Add refrigerant immediately. B. Conduct a nitrogen pressure test. C. Replace the filter dryer. D. Increase the airflow across the coil. Answer. Correct answer. B. Conduct a nitrogen pressure test. Explanation. A significant pressure rise indicates a leak or moisture boiling off. Before charging, it's critical to confirm leak tight integrity using dry nitrogen and a pressure decay test. This step is emphasized in EPA 608 guidelines and ASHRAE 147, which require leak testing before introducing refrigerant into a suspect system. Question 25. Looking at the data on dual-fuel heat pump systems, which control feature determines whether the system will switch from electric heat pump to fossil fuel heating? A. Indoor blower delay setting. B. Outdoor temperature sensor lockout. C. Humidity sensor input. D. Defrost control algorithm. Answer. Correct answer. B. Outdoor temperature sensor lockout. Explanation. Dual-fuel systems often rely on a thermostat or control board with an outdoor temperature sensor that switches heating sources based on efficiency thresholds e.g. below 35 degrees. This prevents simultaneous operation of fossil fuel and heat pump, complying with manufacturer guidelines and NEC 424.3b on electric heating controls. Question 26. By evaluating refrigerant flow characteristics, which property directly influences the ability of the refrigerant to absorb heat in the evaporator? A. Saturation temperature. B. Subcooling value. C. Heat of vaporization. D. Condenser approach temperature. Answer. Correct answer. C. Heat of vaporization. Explanation. The heat of vaporization determines how much energy a refrigerant can absorb during phase change from liquid to vapor. A higher value means more heat absorbed per pound of refrigerant. This concept is core to thermodynamic analysis in ASHRAE fundamentals and plays a crucial role in refrigerant selection for heat pumps. Question 27. As a result of a reversing valve failure, Ista-Kruger's system is stuck in heating mode. The solenoid is energized, but the valve doesn't shift when switching to cooling. What should the technician check next? A. High voltage feed to the indoor coil. B. Suction pressure drop across the indoor TXB. C. System pressure differential across the valve. D. Outdoor fan rotation direction. Answer. Correct answer. C. System pressure differential across the valve. Explanation. Reversing valves require a pressure differential, typically over 60 psi, between the high and low side to change positions. Energizing the solenoid alone does not guarantee valve operation. Refer to OEM valve diagrams and ASE's reversing valve diagnostics for recommended troubleshooting protocols. Question 20. With the advent of smart thermostats, improper setup is a leading cause of comfort complaints. A technician finds that a new Y thermostat was installed on a two-stage heat pump, but only one Y wire was connected. What is the likely result? A. Auxiliary heat will run constantly. B. First stage will not operate. C. Only the first stage will energize. D. The defrost cycle will be disabled. Answer. Correct answer. C. Only the first stage will energize. Explanation. Without a connection to the I-terminal, the thermostat cannot call for second stage cooling or heating, limiting the system to first stage operation. This is common when upgrading from a single stage thermostat without updating the wiring. NEC 725 and OEM thermostat installation guides emphasize correct terminal connections for multi-stage units. Question 29. The effectiveness of auxiliary heat in heat pumps depends heavily on system design. In what situation would auxiliary heat most appropriately activate? A. When defrost is running. B. When outdoor coil is clean. C. When superheat is high. D. When SEER is above 16. Answer. Correct answer. A. When defrost is running. Explanation. During defrost, the system temporarily operates in cooling mode to melt ice off the outdoor coil. To maintain indoor comfort, auxiliary backup heat strips are energized. This logic is controlled by the defrost board and thermostat wiring. Only manual H and OEM schematics confirm this operation for demand defrost capable systems. Question 30. From multiple perspectives, the technician analyzing a two-stage compressor notes that stage 1 operates normally, but stage 2 does not engage. Voltage is present at the control board and thermostat is properly configured. What should the technician test next? A. Pressure switch for the low pressure side. B. Outdoor fan blade balance. C. Run capacitor for the second stage compressor winding. D. Defrost board setting. Answer. Correct answer. C. Run capacitor for the second stage compressor winding. Explanation. Stage 2 compressors or windings often rely on their own capacitors. A failed capacitor will prevent the winding from starting even if control voltage is present. This is a key diagnostic step outlined in ACAT troubleshooting guides and ASE's multi-stage compressor procedures, especially for scroll or rotary type multi-stage units.